Okay, so this is a third and final question. Another great one for us to go over. So this one asks us, we're estimating e to the negative 0.95 using a Maclaurin polynomial. So that tells us that's our code for the center being 0. What is the least degree polynomial that assures an error smaller than 0.001? So with this one, as we get more comfortable with the power series, we're going to kind of know which ones are must memorize. E to the x is definitely a must memorize. And that expansion is going to be 1 plus. Alright, so we got 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial dot dot dot. Now, if we want to set this up in terms of the degree number, we can go ahead and say that this is going to be x to the n over n factorial, and that would give us the nth degree term. So on the last problem I ran through, I actually wrote it in terms of term number versus the degree, and that's because we had sign where there's some 0 terms. On this one we have every term represented, so I'm going to have that n represent the degree of the polynomial term that we're on. Now, once I have this structure and I have this, alright, first thing I should notice is I should notice the fact that unfortunately, alright, I don't have an alternating series. That means I'm going to have to work with Lagrange error bound. Now, in Lagrange error bound, we know that the structure is absolute value of fn plus 1 of z, alright, over n plus 1 factorial times x to the n plus 1. Alright, so at the center, we actually know that that derivative is going to just be 1. And that's why we get the terms that we get along this way, where there's really no change in that front top part of the coefficient, and we're stuck there. But on this, we want to maximize this. Alright, so we want to max this on interval such that z is between our center and the point that we're estimating. We're estimating negative 0.95, and we're going up through our center, which is 0. Alright, endpoints are included, they almost always are. When they're not, then you'd have to optimize over that interval, and to be honest, the time that takes, they'll never ask that as an AP question. Alright, so now from here, we're looking at that interval. We know that the n plus 1 derivative at z is going to be given by e to the z. Alright, because every derivative of e to the x is just e to the x, e to the x, e to the x. So I'm going to take a look at this one, and if I look at that, plugging in z equals negative 0.95, I have 1 over e to the 0.95. Alright, if I look at z equaling the other end of it, which is 0, alright, then I have 1. Alright, so I'm going to look at these two and I'm going to kind of think about them. I have e to the 0.95. Alright, so that's going to take e and it's going to make it a little bit smaller, but not a ton. Alright, so we're still going to be a number probably pretty close to 2. And we have 1 over 2, so I'm just going to ballpark it at a half. Alright, and then we have on the other side 1. Now I'm going to think about what happens as that negative 0.95 gets closer and closer to 0. Alright, so as I do that, I'm going to get smaller and smaller numbers that are closer and closer to 0. So that bottom number is going to kind of creep smaller on me as I move that direction. But it should do it in a uniform way that when I get to a 0 there, I'm actually going to end up at my biggest value overall, because as the denominator creeps smaller, the overall value gets bigger and bigger and bigger. Alright, so that means that to maximize it, I'm going to focus at the endpoint of 0 for that z value. Alright, so if I do that, I know that derivative's 1. So I've got a 1 over an n plus 1 factorial. My x that I'm concerned about is a negative 0.95. Alright, and that's going to be raised to the n plus 1. And I want that to be less than 0.001. Now I'm going to clean this up a little bit. It's absolute value, so the negative really doesn't matter to me. So I've got 0.95 to the n plus 1 over n plus 1 factorial, and that is less than 0.001. Alright, at this point I'm going to lean on technology again. Okay, so jumping to the calculator, I'm going to go ahead and in the top y1 I'm going to enter the left hand side of this inequality, and in y2 I'm going to enter the right hand side of this inequality. Again, I've got a factorial just like the last problem, so looking at the graph really isn't going to be super useful for me, so I'm going to lean on the table. I have my table start at 1 and my table's step size as 1 as well, so I'm going to hit second graph, and that takes me to this table right here. So if I look down the list of values, it looks like we start to get pretty close to our desired goal at 5, but at 5 that ends up being exactly 0.001. Alright, so if when n is 5 we're right at 0.001, we're actually going to have to push past that so that the error is less than 0.001. If I said 5, my error would equal 0.001. Alright, that would be the upper bound for it, so we could have an equals to. So if I push past and I go to 6, that's going to guarantee that I'm less than that 0.001. So our correct answer on this one would be 6. Again, this was a tricky one because you might have some questions as far as, was that really 0.001 or was it just rounded down to that from a value that was close? Because we are dealing with an irrational number with the e, but also remember that e is not coming into play on the left hand side of this, so we are getting that 0.001. So bump it up to n equals 6, and when we're n greater than 5, we get the less than, and that's going to be an n value of 6. Hope that helped. That was definitely a tough problem set. I think it was one of the toughest problem sets that you've had so far. During our Q&A tomorrow, if there's any questions, I'll be happy to answer them.